Now that you understand the meaning of what the derivative is through the limit, we're going to develop some analytic rules that make differentiation easier to do. They're shortcuts, if you will, based on those limit rules that allow us to take the derivative very quickly. We'll start with the constant rule. What you're going to find is that the derivative of a constant function, any constant function, is 0. If c is any real number, then the derivative of c with respect to x is 0. And that's because this function is a horizontal line, and a horizontal line has a slope of 0, always. Let's look at some examples. If y equals 7, the derivative of that function is 0. If f of x equals 0, f prime of x, the derivative of that function, is 0. Let's say s of t equals -3. Well, guess what? S prime of t, 0. Again, because the slope is 0, this function is a horizontal line. Here's an interesting looking one that looks like it might not be constant, but it certainly is. Y equals k times pi squared. A constant times a constant is still a constant. Guess what the derivative of y is going to be? Y prime, 0. Now, the power rule. If we have a rational number called n, then a function f of x equals x to the power n, like x to the third power, for example. It is differentiable because it's a polynomial function. Polynomial functions are continuous. And the derivative of that function, the derivative of x to the n power with respect to x, is going to be n, the original power, times x to the n minus 1 power. This has some powerful implications. If we have a function, say x to the third, then the derivative of that function is going to be some function to the 3 minus 1, or the second power. So when we're taking the derivative of a polynomial, we're always lowering the power by 1. Let's look at some examples. Y equals x. That's x to the first power. So the derivative of that will be 1x to the 1 minus 1, or 1x to the 0. X to the 0 is 1, so the derivative of the function y equals x is 1. Which we know intuitively because y equals x is a line with a slope of 1. How about s of t equals t to the third power? If we use that power rule, we're going to put the 3 in front. It's going to be 3 times t to the 3 minus 1 power, or 3t squared. Okay, now we can have a radical. G of x equals the cube root of x. Now we would rewrite that as x to the 1/3 power. So the derivative of that, g prime, is going to be 1/3 the power times x to the 1/3 minus 1 power. And 1/3 minus 1 is minus 2/3. Another way to rewrite that is 1/3 x to the 2/3. Y equals 1/x squared. Now we'd want to rewrite that as x to the minus 2. So dy dx is going to be the derivative with respect to x of x to the minus 2. And that's going to be -2 times x to the -2 minus 1. -2x to the minus 3, which also can be written as -2 over x to the third power. One very common mistake in taking derivatives using the power rule is to mistakenly add instead of subtract. You're always, when you take the derivative using the power rule, lowering the power by 1. So -2 becomes -3. 1/3 becomes -2/3. So let's look at an example using the power rule. Let's find the slope of f of x equals x to the 4th, which looks like this graph, when x equals -1, x equals 0, and x equals 1. So let's find the slope of that function x to the 4th at all points, and it's going to be, using the power rule, 4 times x to the 4 minus 1, 4x to the 3rd. So that is the function that represents the slope of f of x equals x to the 4th at any point. Let's evaluate it at those 3 points. Well, at -1, we put in a -1 for x. We get 4 times -1 to the 3rd power, -4. And indeed, that's confirmed by the graph here. At -1, 1, the slope is a pretty steep negative, -4. At 0, the slope is 0. If we put in a 0 into this function of the slope, we get 4 times 0, 0. That's confirmed by the graph. We have a horizontal line at 0, 0. And at 1, we put in a 1 for x, we get a positive 4. 4 times 1 to the third is positive 4, also confirmed by the graph. The next rule we're going to look at is called the constant multiple rule. If we have a differentiable function f of x, and we multiply it by some constant, c, that's a real number, then c times f of x is also differentiable, and its derivative is given by c times the derivative of f of x. If we look at y equals 2 over x, which we're going to rewrite as 2x to the minus 1, the derivative of that is going to be 2 times the derivative of 1 over x, which is 2 times the derivative of x to the minus 1. And when we combine that, we get negative 2 over x squared. Let's look at f of t equals 4t squared over 5. The derivative of that is going to be 4 over 5 times the derivative of t squared. So it's 4 over 5 times 2t to the 1, which gives us 8 over 5t. Y equals 2 square roots of x. Let's rewrite that as 2 times x to the 1/2. And its derivative is going to be 2 times the derivative of x to the 1/2, which is 1/2 x to the minus 1/2. And that causes the 2's to cancel out, and we get 1 over the square root of x. If y equals 1 over 2 x to the 2/3, we can split out that 1/2 using the constant multiple rule. So the derivative of this is going to be 1/2 times the derivative of x to the minus 2/3. When we combine that all, we get negative 1 over 3 x to the 5/3. You have to do some simplifying there. Let's look at y equals negative 3/2 x. The constant multiple rule says we can split out that negative 3/2 and x. And indeed, it's going to be negative 3/2 times 1, or negative 3/2. Now, one of the things that's going to help you a lot is rewriting the functions when necessary to make them easier to use the power rule and the constant multiple rule. So if we have y equals 5 over 2x to the third, we can rewrite that as 5/2 times x to the minus 3. That allows us to use that constant multiple rule easily and the power rule. When we differentiate it, it becomes 5/2 times the derivative of x to the minus 3, which is minus 3x to the minus 4. When we multiply the minus 3 times 5, we get negative 15 over 2 times x to the minus 4. And then put that into a nice clean form where we don't have negative exponents. The derivative equals negative 15 over 2x to the 4th. Let's look at another one. 5 over 2x, the quantity cubed. Let's go ahead and split that out so we can have a constant multiple here, 5/8, and then times x to the minus 3. A lot easier to take the derivative of it now because it's 5/8 times the derivative of x to the minus 3, which when we simplify it is going to be negative 15 over 8 times x to the minus 4. We'll clean that up and put the negative exponent where it belongs so we have a positive exponent in the denominator instead. Y equals 7 over 3x to the minus 2. Again, rewrite it, split the constant away from the power term, put the negative 2, make it a positive. It's a lot easier to take the derivative of this now. It becomes 14 over 3x because the derivative of x squared is 2 times x to the first. 2 times 7 is 14. One more here, because 3x to the minus 2 power becomes 9x squared in the numerator. We wind up with 63x squared. We can split the 63 and the x squared. The derivative of x squared is 2 times x to the first, so we wind up with 126x. Let's look at the sum and difference rules for derivatives. The sum or difference of two functions that are differentiable is equal to the sum or difference of their derivatives. That works for either adding or subtracting the functions. And all of these rules that we've looked at follow directly from the limit definition of a derivative. Let's look at a couple of examples. F of x equals x to the third power minus 4x plus 5. A combination of three functions with sums and differences in it. Well, the derivative is going to be the sum or difference of all three of these terms, derivatives. So f prime of x is going to be the derivative of x to the third, which is 3 times x to the 3 minus 1, or 3x squared, minus the derivative of 4x, which is just 4 times x to the 0, which is 4, plus the derivative of 5, you'll recall, using the constant rule, is 0. So the derivative is 3x squared minus 4. Let's look at one more example. G of x equals negative x to the 4th over 2 plus 3x cubed minus 2x. We're going to split those terms up, take the derivative of the individual terms, use the sum and difference rules to combine them. So g prime of x, the derivative, is going to be, for the first term, 4x to the third over 2, which simplified becomes negative 2x to the third. Derivative of 3x to the third is going to be 3 times 3x squared, or 9x squared. And the derivative of negative 2x is going to be negative 2 times the derivative of x, which is 1, or negative 2. So now you've developed some analytic shortcuts to be able to determine the derivative of functions, including the constant multiple rule, the constant rule, power rule, and the sum and difference rules.